Hello, my name is Nicholas Miller, the project manager for the Michigan Technological University Astro-Huskies, and this is our Proof of Life video for the 2025 NASA Lunabotics competition. Next is our faculty advisor to introduce himself and approve this video.
Hi there, my name is Paul Vancesante. I'm a professor here at Michigan Technological University, and I approved this Proof of Life video from the Astro-Huskies team participating in Lunabotics Challenge 2025. Hello, we're here to measure the dimensions of Atlas, the MTU Lunabotics Rover. And we're starting with the length right now. As you can see in the front, it's attached there, the tape to the level. And then in the back here, we have our vertical bar also with the level to make sure it's vertical. And with that, we measure a length of 57.5 inches. We're going to go to the height, and the highest point is in the back here where the camera is attached. And to the bottom of the bar we have 28 and about 8 inches. And then we have the width coming up next, and the widest point is at our wheels here. Make sure we have our bars vertically oriented. And then from one to that one, make sure straight here. And we have a distance of 28 3/4 inches of width. All right, the next measurement is the mass of the robot, the weight of the robot. And so right now we have target to scale to 0 pounds. And now if you guys, 4 of you guys can lift it up and put it on here, we can measure the weight. All right, the vehicle is on there, not touching anything. And it looks like the final weight is 149 pounds.
Hello, my name is Asher Zile. I'm going to show that we're able to switch from a 2.4 gigahertz band to a 5 gigahertz band. There we are.
In this video, Atlas completes a competition run in MTU's lunar regolith chamber. First, Atlas uses its steering system to make a 0-point turn to reorient itself towards the excavation zone. Then, Atlas makes an Ackerman turn around some imaginary obstacles. Atlas's mobility system utilizes 4 linear actuators and 4 motors to both steer and power each wheel independently. The team determined that the increased mobility from a steering system would increase performance during autonomous operations to the point where it outweighed any downsides from the increased mass and complexity. Once at the excavation zone, Atlas deploys its single-chain bucket ladder through the use of a linear actuator-driven 4-bar linkage. As the bucket ladder approaches the surface of the lunar regolith, the deployment speed slows down to allow for proper excavation rates, while the bucket ladder plunges into the ground. This year's excavation system is designed to excavate lunar regolith at a rate of around 18 kilograms per minute. The bucket ladder then transfers the lunar regolith to Atlas's hopper. The hopper consists of a single pitch belt to both store and deposit up to 57 kilograms of lunar regolith in one cycle. The belt is custom made and driven by a chain and sprocket with an extendable frame tensioner to maintain good engagement with the chain and minimize regolith loss when fully loaded. As Atlas excavates, the belt is indexed so the material is evenly distributed within the hopper. After collecting some lunar regolith, Atlas retracts its bucket ladder and reconfigures its steering system once more to crab drive to the construction zone. Once at the construction zone, Atlas spins its hopper belt until all lunar regolith has been deposited into a berm. During this video, all operations were controlled remotely by a student, but the team's goal is to achieve travel autonomy and excavation and dump full cycle autonomy during the competition. Thank you for watching our Proof of Life video for the 2025 NASA Lunabotics competition. We're very excited to bring Atlas to Florida and compete with everyone else.